All right, welcome to General Relativity in Geometric Algebra 2, and in this video we will talk about the covariant derivative and gradient. So this is actually an episode that I'm fairly excited about. I think the math in here is really cool. So let's get into it. Since general relativity deals with curved manifolds, that is curved spacetime, there must be a derivative operator which accounts for said curvature. The and then this derivative operator is called the covariant derivative. The operator should have the following form. Should have the form, should have the form like this. So we denote the derivative, or the covariant derivative with d mu, and then we say that it's the traditional derivative, and then plus there's something called gamma, which is called the connection. So it should be of some form like this, where this is just the traditional derivative, and then this right here is called the connection. And this is what accounts for curvature. So it's a tally for curvature. So the operator should have this form. And how do we figure out how the curvature in general relativity is, how it manifests itself so that we know how to implement a connection? Well, the curvature of I spelled that, it looks kind of weird, but I spelled it correctly. The curvature of general relativity is bound by the following restriction. Restriction. Namely, a coordinate prime infinitesimally close, infinitesimally close to coordinate, I can't write, x, is related via Lorentz transformation, or specifically via an infinitesimal Lorentz transformation. So because the Lorentz transformation is infinitesimal, we have lambda, and then we're going to just denote it with epsilon, where this epsilon is a real scalar value that is infinitely small. And we say that it's like this, e to the 1/2, then we have the infinitesimal value, and then we have the bivector. This is the generator of the rotation, and we're just labeling it mu for now. You'll see why later. And because this is infinitely small, if we expand this out as a Taylor series approximation, we get essentially 1 with something to the epsilon and then epsilon squared. But if it's infinitely small, then all these other terms are going to vanish. Something infinitely small squared is practically 0. So we just have 1 plus 1/2 epsilon omega mu. And of course, just for the sake of consistency or completion, we have that this omega mu right here is a bivector. All right. So now we're going to relate the tetrads of these two coordinates. So if the tetrads for x and x prime are respectively gamma m and gamma m prime, then they are related as follows. Or I'll just say, then we have that gamma prime m is going to be lambda epsilon gamma m lambda reverse epsilon. And this is the condition. This is this condition put into math. It says that the coordinate x prime, infinitesimally close to coordinate x, is related via an infinitesimal Lorentz transformation. So we have x and x prime, which have tetrads, gamma m and gamma m prime. And gamma m prime is an infinitesimal Lorentz transformation of gamma m. So now let's expand this out. We can see that we get this term. Oh, that is not. There we go. So we get this term, gamma m, and then the minus here. And then I'm going to go to right to the second to last line. If you want to expand first this out and then this out, I recommend you do that by yourself. It's a good practice exercise, but I'm going to go directly to this fully expanded, and then I will simplify from there. So from this, we get gamma m plus 1/2 epsilon omega mu gamma m minus 1/2 epsilon. And then we get gamma m omega mu, then minus 1/4 epsilon squared omega mu, and then gamma m omega mu. Now this is going to go to 0 because epsilon squared is an infinitely small value times itself, so it's practically 0. Now we have this factor of 1/2, and then we have objects swapping order and a minus sign. So this is the definition of a commutator bracket. So we have gamma m plus epsilon, and then omega. I can do a better bracket than that. Omega mu gamma m as so. Cool. So this now is the result. This is gamma m prime is gamma m plus an infinitesimal rotation. So this right here, this is the infinitesimal rotation. And we can think of this as the curvature tally. So now that we have the curvature tally, we can define the covariant derivative, because recall, we just need the curvature tally and we can just slap it into this equation. So therefore, the covariant derivative is defined as d mu plus, so it's partial mu plus the commutator of the generator of the rotation, and then whatever object you're differentiating. So we don't have anything here or here, so that's why we have nothing here. And this is the definition of the covariant derivative. So then, what's the covariant gradient? Then the covariant gradient, and you'll see there is a difference between the covariant derivative and covariant gradient. And this is a distinction that maybe not everybody makes, but I like to make this distinction. And it is d equal to g mu partial mu. So now this is a scalar quantity. And this will give you a scalar quantity. So like if you, or this is a scalar quantity here, so it preserves the grade of whatever it acts on. However, this is a vector quantity because this is a vector, and now you're summing over the vectors with a scalar. And just for the sake of consistency, so you can see what it looks like, all expanded, we get this. And this right here is the definition of the covariant gradient. Oh, and I'll just, so that you can recall easier, where G mu is the reciprocal coordinate basis. It's the reciprocal coordinate basis. And so normally I'd say, this is it, we're done, we've done this all. But let's talk a little bit about how this would look in the traditional geometric calculus notation. So in geometric calculus, it looks at like this. We have d is going to be equal to the derivative with, or the gradient with respect to a. So what a is an arbitrary vector, and then we get the spacetime gradient dotted with a. So now the spacetime gradient in the direction of some arbitrary vector a plus this quantity right here, where now we have the generator, but the generator, loosely speaking, looks slightly different. It depends on this arbitrary value of a, whereas here we can kind of think of that mu taking account for this in this equation. And this is what it would look like in geometric calculus. And we can see how these are equivalent as follows. I'm going to now, to show equivalency, I'm going to expand, or let's continue in the royal we. We will expand the g mu partial mu into the same form as a, or partial a dotted with the partial. And you'll see the reason why I'm only doing this into this is because they're just the first terms here. So I'm going to show that this term is equivalent to this term. And you can do the same thing for here and here and here and here, but I'm just going to do it for here because it's a less lengthy calculation. So we have g mu partial mu. And the definition of g mu, recall, is partial superscript mu and then the coordinate x, where that's a vector in the spacetime algebra. And then we can expand out the vector in its basis. So we can say it is x nu gamma nu. So if we sum over this independently of the mu's, then this gives us the vector x. And then we have partial mu right here. Okay, so now we're going to rearrange, because now when we're dealing with tensor notation or Einstein summation notation, we can just kind of rearrange things. as long as they're not multivectors. So this is scalar, this is scalar, this is scalar, this is a vector. So we can kind of move these all around as long as we remember that this acts on this. We just need to remember that. So at the very end, we can put things into the correct form. So we'll rearrange by moving things like this. We have partial mu, gamma nu, and then we have x nu, and then partial mu, like so. And then expand, or now what we're going to do is swap the index here using the Minkowski metric. So we get partial mu, and then we get gamma mu. And now we have to pull out a Minkowski metric here, because you can see that if we sum over the indices here, then we raise this gamma to have a nu. And then we have x nu partial mu. And now we're going to sum over this nu. So this is going to be the same. And now we have x mu partial mu. Well, this is just the definition of the space-time gradient. As we saw in the last video, or the very first video, this right here, this is the definition of the space-time gradient. So we're now going to plug that back in. So we get space-time gradient of, and then this is just the x component with the appropriate partial component. This is the inner product of two vectors. If this is the vector of the space-time gradient, and this is just the coordinate vector, then this is their inner product. So we get x dotted with d, like this. Now, recall that the space-time gradient is just the gradient with respect to the coordinate. And so we can just rewrite this for sake of consistency in this form. And this right here is what is equivalent to partial a partial. And so you can see that the traditional Einstein summation notation ends up with the same result as the geometric calculus notation. On the next video, we'll be talking not about tetrads or covariant derivatives, but instead about the connection coefficients. So we'll be talking a little bit more about this guy.